Alright, here we are with our final few levels of Nandgame, where we should be taking everything we've created so far to build a fully functional computer. So here we are at combined memory. So last time we made our RAM or random access memory, and so what are we doing with our combined memory here? Let's see, a processor uses both kinds of memory, registers and RAM. Registers are directly accessible by the processor and can be used for intermediate values and calculations. RAM can store a large amount of data, but we can read or write from only a single address at a time. This processor will have two registers called A and D and one RAM bank. In this mission, combine the two registers with the RAM bank. Okay, so essentially we've got two registers for A and D, and then so basically when A is on, we write X to the register, and then D, we write X to the D register. Okay, it's easy enough, suppose. Okay, so we got RAM with certain addresses, and I'm guessing we're going to need two registers for this, an A register and a D register. So do we have a selector here? No, but I think we might not need to, because these two flags, A and B, connect as the store conditions for these two registers here. We'll just write X to both, inputs here, then get our clock going here. Oh, okay. I see what it's doing. So this is the A register, this is the D register, so we might not even need registers here. Okay, yeah. So we just got X, got our clock, and AD. I completely forgot what that was. Let's see if we can figure it out. Value. Okay, so that signifies which address it's the address flag. Okay. Let's see. Move this again. Oh, no, I don't want to spoil myself not looking. I thought that was just going to give the introduction. Maybe we don't need... Yeah, okay, I'm just going to start off with what I know here. We've got our A register. And the A flag is clicked. We write X to, let's call X 42. And then clock. Setting it to the A register. Okay. So, okay, we write X to the A register with the A flag. D flag is write X to the D register. And then star A, write X to RAM at the address given by the A register. Okay, so we're just going to use two registers for A and D. Easy enough. We're going to change this to 5012. 21. Oh, let's get the D output going. And clock. 5021 is now stored in the D register. Let's bring these up a little bit here. And then star A is we write X to RAM at the address given by the A register. So whatever the value of the A register is now the address in RAM. So put the address there. Oh, okay. I was wondering if it wasn't going to work because I thought maybe there's only 4 addresses total. But yeah, okay. So whatever value is in the A register is now the address in RAM. And when A star is I guess, indicated or flagged, you write X to the RAM at the address given by the A register. That makes a lot of sense. So now if we flag A and hit clock, that should store 5021 and address 42 because 42 is the value of the A register. 42 and 42. Yeah, 5021 and address 42. Yes. Yes. Okay. I don't know if I really need to clean all this up right yet. But I will do if I need to deconstruct it in the future levels. This looks like our next level is instruction. Interesting. Okay. I as an instruction to the ALU. I apologize that I'm not talking more about like the specific real-world ramifications of this. My education was mostly dealt with the circuit construction, so like I never really got too deep into instruction combined memory. That would be more on the computer engineering end, which I barely touched on. This is very interesting to learn on about. I is an instruction to the ALU and condition components. The bits direct the operation as specified. So yeah, essentially, whatever bit instruction is sending flag. Okay. I is in the instruction when bit 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0 is on, it tells this group to mark that flag. Okay, so that, assume splitter, and we're only concerned with these bits here. So we've got our ALU to the U. Wait, what? Let me just finish reading all the instructions here. The bits direct the operation as specified. We got ALU, destination, and condition. The XAD and star A inputs are the values of the registers. The X input to the ALU should be D. The Y input should be either A or star A, depending on the bit 12. On bit 12 in the instruction, if bit 12 is 0, A, if 1, star A. Okay. Our output is the result of the ALU operation. Okay. And the J flag indicate if the ALU output conforms to conditions specified in bit 0 to 2. Okay. The bits direct the operation as specified. If bit 10, we mark the U flag on the ALU. And that goes to the result. Bit 9 is op 1. Bit 8 is op 2. No, I mean op 0. 7 ZX. Okay, this seems, yeah, fairly easy. Switch for 6. 5 is destination. R is the result of the ALU operation. The X input should be D. Okay. And then Y should be either A or A star. If bit 12 is 0, it's A. So by default, it's A. But if bit 12 is 1, then we do star A as our Y value. That is a mess of wiring here. Let me just get this down here, out of the way-ish. Okay. So that should take care of those values. Destination A, D, A, star. Okay, yeah, I guess just... Okay, just so J should be the output of condition, and 5, 4, and 3 just go to A, D, and A star accordingly. Let me just test that out. What would be a... Let's see. 1, 2, 4, 8, 16, 32. And yeah, so just one number there. So doesn't need to worry about it. We don't need to worry about that too much. Then D, A star. And for our conditions, less than, equal to, greater than, less than, equal to, greater than. And then X is D, so let's... Can I connect it? Oh, maybe? No, okay. I thought I might have been able to connect it to that node there, but no, I just got to bring it all the way down again. A little disappointing, but what can you do? Let's just pretend. There we go. So, yeah, that I'm not going to go through every single possible operation because I'm fairly sure this is correct. No. Okay, what's going on here? When I is negative 2096. Okay, what is... 96 J is 1 when it should be 0. Wait, yeah, let me just... A star is 42. R... Wait a minute. Instruction negative 2096 F4A6. Oh, 2906. There we go. 2906, 42. A is 1, and J... Huh, did I mess something up here? 2 and 1. Why would it be 0? Did I mess up there? JFlag indicates LU output conforms to conditions specified in bit 0 to 2. Okay, so it's not just the output of the conditions. It specifies that conforms to the conditions specified in bit 0 to 2. It should... So that should be 0. Why? Less than, equal to, greater than. X input to the ALU should be D Y input. Okay, so that's right. 0 greater than J flag indicate if the ALU output conforms to the condition specified in bit 0 to 2. Yeah, so why is it 0? It's both less than and equal to 0. Where am I going wrong here? Six, 543 to destination. J. It's right for everything else except, well, almost everything else except for negative 2906. Why? That's the result. I am very confused. Pausing this order. Sorry, so 0 J. Yeah, that looks like this is all sorry. I'm still on the second level. Um. Hmm. Our output is a result of the ALU operation. J flag indicates if the ALU output conforms to the conditions specified in bit 0 to 2. Oh. Okay, I think I know what that might mean. It means whatever the output of the ALU is should conform to the conditions here, not... Oh my god. Okay, that makes sense. Let's see. Yep. Okay, I was thinking too literally about what X was supposed to be. X in the ALU, not the conditional, but I assume they should be the same because I didn't see anything specifying the conditional. But it's right in front of me. The J flag indicates if the ALU output conforms to the condition specified in bit 0 to 2. So, yeah. 2A or 42 is not less than or equal to 0, so that becomes 0. Good, okay. 3 components used, not counting splitters. Oh god, I don't know if this means that. Oh god. Does it say it's possible to solve using fewer components? So I'm going to say that this is the simplest it can be. Because I don't know how we could make this any simpler. Got these two. Yeah, there's no way we could, yeah, there's no way we could change that. Okay, next level. Control unit. Program is a sequence of instructions. Each instruction is a set of bit flags to determine the operation, an ALU operation to perform, which registers to use the input, and which registers to store the input in. Okay. So we have our instructions, we have our memory, And now we can put that all together to build a control unit that, based on whatever instruction and registers you get, gives you a certain output. So, data, okay. In addition to ALU instructions, the computer should also support data instructions. In the data instruction, the instruction value is directly written to the A register. So that's this. No, these are all 1-bit values directly written to the A register. So I'm assuming, yeah, that's just the register. If it's a data value, we're just writing whatever the instruction value is to the register. Okay. So if bit 15 on instruction I, let me just, so if that's high, if it's low, it's data. Wait, so if it's 0, it's a data instruction, which means we just bypass all the logic and write it directly to the register. If it's 1, it's an ALU instruction, which means our input to that selector is the output of the ALU. And let's bring all these flags down here. Let's bring this off to the side a bit as well, so we can get that instruction value and A, D, A star, and yeah, that should, yeah, or as a result of the ALU operation, and that only goes through if 15 is high. Any others, I should just pass the instruction directly, directly to the register. Yep. Okay, that should be it. No. Okay, what am I missing here? 1, 2, 3, 4. A should be 1, D should be 0. Okay. That is... Wait, what else was there? A is 7. D is 9. And 13. D should be 1. Why should D be 1? I might have to look back at the previous level. Oh, I forgot the J. That doesn't change anything. Okay. I'm gonna quickly go back to the previous one, put in 1, 2, 3, 4. Okay, yeah, that turns on bit 4, which is destination D, not destination A. So why is that incorrect here? ALU instructions, selectors, why? Did specify differently what data instruction. The instruction value is directly written to the A register, create a control unit which execute either data or ALU instruction. Depending on the high bit for ALU instructions, the output should be specified. In the previous level, R for data instruction, the output R should be the I input, and the destination should be the A register, i.e. A should be 1, everything else should be 0. This is why you always read the instructions first. Read, read, read again. That old adage, measure twice, cut once. Oh, God. I rush into things way too quickly. So, if it's a data instruction, then I guess we have another select. Maybe. If a data instruction, then maybe not. Maybe some Nands? Let's try that actually. Because if it's A and... No, that wouldn't make any sense. Oh my god, come on. If 15 is on, then you ignore A. Wait. Oh yeah, because this is destination A, D, and A. Register. If it's data instruction, this is 0. Then if this is 0, then we can make come on. Talk it through, talk it through. Unless this is 1, then only A is 1. And if this is 0, everything else is 0. Okay, yeah. I'm worried I'm going to overcomplicate it by putting a bunch of things together. If I do, I'll just go back and optimize. If 0, then we default to 1. If 1, then A, D, or A star. No, 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 no. A should be 1. All other flags should be 0. Okay. Just, gotta clear this out. If it's 0, then it should be 1. If it's 0, then A should be 1. And if it's 1, then D, A, and J. So, yeah, if it's 0, then God, yeah, okay, don't worry about overcomplicating it yet, just make it work. If it's 1, then, come on, connect. Connect. Okay. Come on, connect. There we go. So this is now set up to where if this is 0, then it will be default to A, but if it's anything other than 0, for example, let me just go F. Then it just defaults to what those other registers are actually. Okay. So yeah, I genuinely, I don't know at the moment if this can be simplified any further, but yeah, looks like that works. Onward. Oh really? This is the final challenge? You can complete this, you've built a working programmable microprocessor. Oh no, we got one more. Okay, so here we are. Build a computer by combining a control unit, memory, RAM, and registers, a counter, which keeps track of the current instruction address, and a clock. So, first and foremost, we'll send the clock to everything that requires it. And our control unit, our destination, will be the inputs of our memory here, A, D, A. Our result will be X. A, D, A. And the instruction, let's see. The word at the PC address in the program memory is the I input to the control unit. Okay, so one of these outputs is going to be I. Each clock cycle changes the program counter depending on J. Okay, so if J is on, then we... Come on. Change that there. If J is 0, the program counter should advance with 1. If J is 1, the PC should set the value on A. So... J is 1, it should set to the value on A. Okay. It's the control. The word at the PC address in the program memory is the input. So that's A star. And counter okay. Program counter PC, the word at the program counter address in the program memory is the input to the control unit. I don't think we need ROM, which is just read-only memory, a set of instructions to... Oh no, yeah, this is exactly what we need. And then our output to the ROM will be the instruction. Okay, let's reset everything. So our read-only memory will be the instruction, which affects the control unit, which will write it to memory, and then our memory will be the inputs to our control unit, which, so let's close there. The counter will increment the ROM instructions. So yeah, that should be, yeah. Okay, that's it right there. The simplest possible solution. Awesome. Okay, so yeah. So we have a read-only memory here, which contains a set of instructions that go incrementally based on the clock cycle. The output of our ROM becomes the instruction for our control unit, which, depending on whatever values are in our A, D registers, or the address, which is what the star A represents, will cause us to write memory into, which will cause us to write to our memory, and then just keep going from there. So that is that, and now our final level is input and output to be of any use. A computer needs to be able to communicate with the outside world. This happens through hardware devices such as screen, keyboard, touch sensors, network interface, and so on. In this level, we integrate with simplest hardware devices a lamp and a button. Okay, connect a lamp and a button so that they can be accessed like a memory address. The lamp is controlled by bit 1 and 0 of X. When bit 1 is 1, the lamp will get a signal to be on. When it's 0, it should get a signal to be off. Signals should be sent to the hardware when store, so that's our output hardware. When store is 1, and the clock signal is 1. Okay, so we're going to have our AND gate here when both clock and store are 1. Then our output will be sent. Both store 1 here. Okay. The button state is shown on bit 15 of the component output, so we'll need a splitter for that. When the button's pressed, bit 15 should be 1. Oh, okay. I see. Bit 15 should be 1. When it's off, it should be 0. Input signal should be readable immediately. Okay. I believe that's it. No. May need an exclusive OR if we have one, but we're not given one, so it probably won't be necessary. When bit 1 is 1, the lamp should get a signal to be on. When bit 0 is 1, the lamp should get a signal. What was the actual problem here? Current diagram does not set bit 0 to 1. Oh, wait. When bit 0 is 1, the lamp should get a signal to be off. When store is 1, signal should be sent to the hardware. Okay, so yeah, we're gonna have another selector here to this AND gate. Just bring this off to the side a bit. And I guess we can bring our button over here. Store and clock are on. Okay, yeah, we'll need 2 selectors here. Here and here. The current diagram is not going to expected output to be 32768, but with 0 when the button is pressed. Okay, what did the button need to be? When the button is pressed, bit 15 should be 1. Oh, signal should be sent to the hardware. This is the hardware. This is not. So we don't need this. Signal should be visible immediately. So go. Yes, okay. So here we are. So yeah. Signals. Input signal should be readable immediately. So there we have it. We've got our button and our lamp. A bit underwhelming compared to the computer, but it's a good introduction towards how physical hardware interacts with all the circuitry in the computer we have made through these levels. I want to thank you very much for sticking through me with this series. I can bet it was probably frustrating watching me trudge through things that may have probably been very obvious in hindsight, but yes, thank you very much for sticking along with me. I'm not sure if I have any other series ideas at the moment, but if anyone thinks of anything that might be interesting for me to make a series or at least a video on, please let me know. And yeah, thank you.